All right, let's get started. This is the first semester exam review for astronomy. Your exam is on Thursday of this week, and it is going to be third block, right? What you receive is you'll receive a multiple choice exam with a cover sheet. Now, the cover sheet, you should put your name on the cover sheet and read it. And notice what is written not only to the student, but also to the proctor. Hopefully I'll be there to collect it, so that's not going to be a problem. But in the case I'm not, make sure you understand what the proctor should do when you hand it in. Make sure that your name is not only on the answer sheet, but on every page of the answer sheet. Make sure your name is on every page of the answer sheet, and as well as the cover sheet. Okay, now, what I'm going to be doing is, there are 120 multiple choice questions, and that's it. Now, I want you to stay busy. Take it slow. You have 2 hours. Some of these questions you can do in seconds. Some will take you a couple of minutes. Either way, you have plenty of time. And with this review, I think that you'll have a lot of time left over. So, this is what I propose. Take the back of the answer sheets and draw a picture representing something. Either Kepler's view of the heavens, do a mathematical example using Kepler's laws. You can look that up. Do something. Do something on constellations. Something relative to astronomy. Relative to, think of an essay, but put it in picture form. You write your own essay. And how do you, well, what do you know? I mean, how do you know what essay to write? Well, you could write something on satellite motion. You could write something on light. You could write something on polarization. You could write more than one, but do it in picture form, okay? We'll be right back. We have a guest speaker here, Professor Don.
Mr. Randall Photobomb or Audio Bomb.
All right, so I'm back after my very quick meeting with Professor Don Quixote Randall. Now, I'm going to use Form B, so it's not going to go necessarily in the order. I guess it will. No, it's not going to go in. Well, I guess it will. I don't know. Whatever. Anyway, let's start. All right, so there are 22 true and false. Now remember, I'm taking this right out of the book, so use your text from online. I'll just tell you what the first question is, show you how fair this is. Don't you hate it when a teacher says something's really fair? Well, why is he saying that? Maybe it's not fair. Maybe he's like fooling us, but it is fair. I'm going to tell you what the first question is. Remember we did shadows, and we talked about umbra and penumbra. Remember that? Question 1. This is true or false? I'm not going to give you the answer. It says a total shadow is called an umbra. True or false? So we're going to look at satellites. Okay, we're going to look at ellipses. How do I draw an ellipse with a pen and paper? What other things might I use in order to draw a perfect ellipse? Not a circle, although a circle, I suppose, is a type of ellipse. If you take that circle, remember we saw that film? If you take the circle and kind of sit on it, the center kind of separates, almost like a cell dividing, where you get two nuclei, where you get two centers with two separate radii. So you have satellite motion. You need the whole concept of an ellipse. I'm going to give you a vocabulary word. Apogee. A-P-O-G-E-E. Remember that word. So we're going to look at satellite motion, frequency. What's the difference between frequency and period of satellite motion? What's a light year? What is inertia? What are the 3 laws? They're very important in understanding any kind of satellite motion, any kind of motion whatsoever. If you take friction out of the equation, things become very simple. It's the friction that really kind of is a bit of a drag, no pun intended, but friction is tough. So what causes a rocket ship to travel? How does it work? There's nothing to push off against. We're going to talk about what light is. What did Einstein have to say about light? What did he win the Nobel Prize for? That's a hint. Infrared, ultraviolet, X-rays, again, some more satellite motion. A quantity that has only magnitude. What is that? What's the difference between a vector and a scalar? Remember we talked a little bit, we did a little bit about absolute value and things like that. If I didn't, remind me, and I'll do that today. I'll do a little bit today. Scalar versus vector, that's important. Polarization, what is polarization? If I have a road, I'm driving down a road, and I get the glare from the road, is that horizontal or vertical? Is that horizontal or vertical? And if I have polarized glasses, which way are the polarization lines on the glasses? Okay, now we got multiple choice. Multiple choice runs from 23 to 120, so it's about 97-ish, my math's correct. So we're talking about electromagnetic radiation. We're talking about the velocity versus acceleration. If something is, if there's a force that's accelerating a rocket ship, what happens if I take that force away? What happens to the rocket ship? What do I do to slow it down? Orbital speeds. What about color? White. What is white? Why is the ocean blue? We're talking about a space shuttle. The orbit of a space shuttle. Space shuttle is nothing more than a satellite. Jupiter. Okay. What's the relationship between the radius of Jupiter, the mass of Jupiter, and the gravitational forces of Jupiter? So remember, now we're talking about universal gravitation, not just satellite motion or forces. So when you read through the book, look at chapters 3, which is inertia and projectile motion. Look at chapter 4, which is linear motion, and then chapter 5, which is Newton's second law. Chapter 6 is Newton's third law, and the chapter on satellite motion, light and color, universal gravitation. Now, I took out all the questions. I mean, when I made this, I didn't put any questions in that are very, very, very specific to the study of physics necessarily. It's how Newton's laws relate to space travel, either by a satellite or by traveling to the moon. So there's not a lot on friction, although, I mean, you got to know friction, but it's Newton's laws, basic laws, relative to interstellar travel. Maybe someday we'll have that. Action-reaction, for instance, with Newton's third law. If I fire a cannonball into frictionless space, transparent, opaque versus opaque, a little bit on friction relative to, If I have, let's say I do go skydiving. Do I do I accelerate towards light speed, or what's terminal velocity? What's terminal velocity? What's the period of a satellite relative to the frequency? I think I said that. Why are sunsets red? If I have a hammer and a feather in a vacuum, do they fall at the same speed? Do they fall at the same time? Some simple calculations. I didn't do some essays, but I put in some simple calculations. A jet that has a mass and it has a force, thrust, what's its acceleration? F equals ma, very basic. What about universal gravitation? What's the equation for universal gravitation? Put that in your notes. You could literally write an essay just based on the equation, coming up with examples, etc. If I have a projectile motion in a vacuum, for instance, what does the line look like? Well, it's very parabolic. If you don't have that, remember Tartaglia, where you had that air resistance, and it started off kind of as a parabolic shape, but then it kind of went up, and then kind of like, the first half was parabolic, but the second half was kind of cut off. It kind of fell more straight down. Curve was more sharp. What is the relationship between radius of orbit of a planet and speed of orbit? Let's go look at shadows again. Umbra versus penumbra, sharpness of something. I have, human sensitivity to light. What color are human eyes most sensitive to? What has more mass? A kilogram of feathers or a kilogram of iron? It's kind of interesting. Here we have more vector stuff, some gravitational things, where you have the universal gravitation equation. Again, some more, remember F equals ma, there's some calculations, but it's not any more complicated than F equals ma, or the universal gravitation equation, or the product of the frequency and the wavelength of light equals the speed of light. We talk a little bit about clouds and the color of clouds. We look at the what is a color? What is a color? Again, here's some more about satellite motion and elliptical orbit. Here I have terminal velocity, gravitational field strength, that's the equation for universal gravitation. Trampoline, if you're jumping on a trampoline. Don't forget Newton's third law. Let me look at that. Let me give you that quick question. You and a friend are jumping on a trampoline. Why does Earth, which is rapidly orbiting around the sun, not move under your feet when you jump? That's a little odd. It's very odd. Suppose the gravitational force between two massive spheres is 100 newtons. Again, that's the force, it's universal gravitation. And the distance between the spheres is doubled. What happens to the force? Okay, so we talk about a little bit more about color. Talk about the moon, the relation between the moon and the earth. Heat lamps, again, that's more like different types of electromagnetic radiation. What is electromagnetic radiation? Where does it come from? All right, we'll be right back. We have to do some work here. Hold on. You actually learn that in chemistry class, electromagnetic radiation comes from transitions within the atom, electrons that are excited for whatever reason. They go up X number of levels away from the nucleus, and then they automatically calm down when the excitation energy, what is it that is making them excited to move away from the nucleus? So when an electron is excited, it moves away from the nucleus, it moves into a higher orbit. And then when that excitation energy is no longer there, then it will automatically, well, it can do it when the excitation energy is there, of course, but it will fall back towards the nucleus, giving off what you call a quantum of energy. That quantum of energy, quantum means packet, that package of energy is light. It's electromagnetic radiation. So that's where light comes from. And light is not just visible light. Actually, visible light is a very small portion of the electromagnetic radiation spectrum. You have radio waves, microwaves, you have infrared heat waves. Then you have the visible spectrum, Roy G. Biv, going from the infrared, red, orange, yellow, green, blue, indigo, violet. Remember, yellow, green is the light that our eyes, human eyes, are most sensitive to. Bees oftentimes are ultraviolet. You don't see bees oftentimes on a rainy, stormy day or a cloudy day specifically. We're talking about, here's some more with the third law, Newton's third law. A 10-kilogram brick and a 1-kilogram book are dropped in a vacuum. The force of gravity on the 10-kilogram brick is what? Then we're going to talk about the relationship between the Earth and the Sun. What happens what would happen? The moon revolves around the Earth, right? What would happen if the Earth disappeared? All of a sudden disappeared. What would happen? What would happen to the moon? What would it do? Kind of wobble around, not know what to do? No, where's my Earth? Well, what would it do? That's a question. The elevator, if you're in an elevator and you have a weight, let's say the elevator is sitting on the ground floor, right? My weight is, let's see, I'm 100 kilograms and my weight is 1,000 newtons. What would be my weight if the elevator is not moving? Well, 1,000 newtons. All right, now, the elevator is accelerating upward. Accelerating upward. What's my weight? Is it higher or lower? It starts accelerating and then hits a constant velocity. What's my weight? Higher or lower? Now it descends. Accelerates downward. What's my weight? Higher or lower? Now it's descending and it hits a constant velocity. What's my weight? Higher or lower? As I, like the, what's the acceleration due to gravity on Earth? Well, it's 9.8. We say 10. What is it in the space shuttle when the astronauts are floating around, weightless? What's the gravity? What's the acceleration due to gravity? What is free fall? What does that have to do with inertia? When they don't, they're just floating around. What does that have to do with inertia? If I shoot a projectile horizontally off a tower, and I shoot it fast enough, what could happen? Let's say there's no gravity, or it's minimal. If it shoots so fast, what would happen to it? Maybe you're going to have to do some calculations relative to projectile motion, horizontal projectile motion. Maybe you want to look at a video to kind of dust off. Remember, there's three things you have to look for. There's three variables. There's the dx, the distance it goes, the horizontal distance it goes, the horizontal velocity it starts at, and the height of the tower. Those are the three things. I'll give you two, and you have to solve for the third. What is the relationship between the time it takes to travel horizontally and the time it takes to fall vertically? If I shot a projectile horizontally at the same time I dropped a penny vertically, what would hit first, the penny or the projectile? Again, another gravitational force problem. Here's one. You drive past a farm and you see a cow pulling a plow to till a field. You have just learned about Newton's third law, and you wonder how the cow is able to move forward if the plow is exerting an equal and opposite force on the cow. Which of the following explanations, or which of the following explains the movement of the cow and the plow? Again, here's some more polarization. How do you test? If you're in a store, say you go to Carrefour and it says these glasses are polarized, how would you test whether or not those glasses are polarized? You're sitting in your chair right now. What's your weight? You stand on a scale. What's your weight? Is it what you read? What is the scale actually reading? Is it reading your weight or what? Let's see. Again, here's some more universal gravitation. Now, these are all mixed up, where in the Form A, they're not. So that's why I keep going back and forth, which I prefer to go back and forth. What's the relation between the altitude of a satellite and its period, its frequency, and its speed? Let's see. What did Newton think of the moon? What was his ideas of the moon? What did he think? You got to know Copernicus. You got to know about Copernicus, Newton, Tartaglia. Remember the scientist report? You got to know those guys a little bit. Not much. Just, don't go crazy. Here's a projectile shot vertically. Absolutely, positively vertically. Not like curve, but just up and down. That's a good one. I like that. Let's see. Talk about clouds. Here's another about weight. Copernicus. Ball is thrown horizontally. Satellite, circular orbit. Again, another universal gravitation. And that's it, really. I just went through it. I went through all 120 problems and talked about them. So I would strongly suggest looking at this, listening to the video, maybe using it to help you write up your sheets. Now remember, let's just review quickly. Remember, you're putting your name on everything, right? Make sure you clearly, leave a little box blank at the top of your paper, and put your name, or better yet, take a highlighter, one you can see through, obviously, and put your last name, big letters, across the front of each one. You have two papers, remember, you can do two, and they've got to be handwritten. They've got to be handwritten. They cannot be typed. And you put your name across them, all the way across. And, in big letters. So I know whose they are, because they're going to be collected in two piles. The credit and then the extra credit. Obviously, the credit should be the one that's the biggest or the most comprehensive, has more writing on, and you'll get a grade. So you're going to have 2 A4 pieces of paper, 8.5 by 11 sheet, same thing, basically. And you're going to have your name across it. So, anyway, that's the story. So you're going to put your name on you're going to put your name on the cover sheet. You're going to put your name on all 3 pages of the answer sheet. You're going to put your name, big, bold, block letters across the front using a highlighter so you can see through it, obviously. Okay? All right. And get all that done before Thursday. So, so you'll know what to do. You'll be given your exam. Make sure you read the instructions, not only for you, very basic, do your test, but also for the proctor so you know what's going on. And make sure you do your drawing, a little essay. I'll give you extra credit for that. And you have a good one. Some of you are going to need it. I don't mean to sound aggressive, but make sure you look at chapters 3, 4, 5, 6, 7. Is that right? Yeah. Not crazy. This isn't a physics course. Satellite motion, light, and universal gravitation, and you're going to be good. You'll be good. And look at this video, and ask me questions today. I want you to go over, to a large degree, I want you to go over this video. So that's one of the things we're going to do today, and you can ask me questions, because we have 80 minutes, and this video is, 30 minutes at the most. All right, talk to you later. Have a good day, and goodbye.